Swayam Prabha. Digital India. Educated India.
So, good morning all of you. So, yesterday we were looking at internal flows. We started with the basic introduction about the fundamentals of laminar internal flows. So, I was talking about the growth of the laminar boundary layer, the hydrodynamic boundary layer from the different walls of the duct, and at some point downstream from the entrance the boundary layers merge, and that's what is called the distance where they merge from the entrance of the duct is called the entry length, okay, the hydrodynamic entry length. And beyond that you will find the entire region is dominated by viscous effects, okay, and also the velocity profiles. If you draw somewhere downstream of the region 2, you will find that they take the shape of a parabolic velocity profile. So, how do we know that this is parabolic? We will derive the from the basic equations. We will show that it is a parabolic profile. And apart from that, if you also have an associated heat transfer either in form of a uniform temperature or a uniform heat flux applied onto the walls of the duct. So, you can say either this is constant Q wall prime or T wall is constant. In this case you will find a temperature profile, so where the temperature is higher at the wall and is minimum at the center of the duct. Now, the criteria for defining these three regions 1, 2, 3 that I have indicated here. So, in region 1 the velocity profile keeps changing along with the axial position, okay. So, therefore, this is a region where we cannot make much approximations in the Navier-Stokes. Once it merges here, so once the entrance length is reached where the two boundary layers merge, if you plot the profile on from there onwards, you will find that it is a parabolic profile and it is invariant of the location downstream. So, therefore, for regions 2 and 3 you can put a criteria that du by dx is 0. That means the profiles are invariant of position downstream, and this region is called as hydrodynamically fully developed region, okay. And when it comes to the temperature profiles, however, as you can see that when you apply a uniform heat flux or a wall temperature, you keep on supplying energy, and therefore the wall temperature keeps changing, keeps increasing along with the location. Simultaneously the fluid which is receiving heat from the wall also keeps increasing in its temperature profile. Therefore, you cannot put a similar criteria saying that dt by dx is 0, because dt by dx will keep on changing because of continuous heat addition. Therefore, we have to look at a non-dimensional temperature theta, which when defined in this particular fashion, T minus T wall by T mean minus T wall. So, here unlike the external flows where you use the free stream temperature as the reference, we have to use a new reference temperature which we call as a mean temperature or bulk temperature or the mixing cup temperature, and we define the mean temperature. We derived this yesterday based on that if you replace a non-uniform temperature with a constant or a uniform temperature which we call as T mean, so the enthalpy of this and this should be the same, okay, because this is a flow process. So, therefore, we talk in terms of enthalpy rather than internal energy. So, for that condition you get an expression for the mean temperature or bulk temperature, which is nothing but mass weighted average temperature. You see this is the temperature and this is the mass. So, you are giving a mass weighted average at different locations radially, and then you are summing or integrating them together. Okay, so this is how you define a mean temperature and therefore condition on theta. Okay, now the condition on theta will be, now your wall temperature will be only a function of x, and so is your mean temperature, because you are averaging out along the radial direction. So therefore, if you look at the numerator, so this T minus T wall will have a certain variation along x, which is exactly similar to the variation of T mean minus T wall. So therefore your theta as a whole does not have any variation with respect to x. Okay, so therefore theta will be only a function of r, right. So therefore we can put a condition that if it has to be thermally fully developed, then d theta by dx should be 0. So that means theta should be only a function of r. Okay, so therefore if you plot the non-dimensional temperature profile, it will look very similar to your velocity profile. So where it will go 0 at the wall and you get some kind of a profile like this, and this will remain invariant along the axial location. Okay. So we also showed that if d theta by dx has to be 0, consequently the heat transfer coefficient in region 3, okay, where it is hydrodynamically and thermally fully developed, has to be a constant, irrespective of what thermal boundary condition that you use, whether it is a constant wall temperature or constant heat flux. Okay, so this is a very important condition that you get in internal flows, which is unlike the external flows, where your heat transfer coefficient is a local heat transfer coefficient and it keeps vary continuously. Okay, here once you get a fully developed profile, both hydrodynamically and thermally, the value of heat transfer coefficient has to be a constant. So we will have to see now what is this constant value, and it depends on the boundary condition. Okay, so the next couple of lectures we will focus on only the region 3, which is the simplest region to start with, where you can make approximations with respect to the velocity as well as the temperature profiles, and we can derive the expression for it is just a value, constant value for the two different boundary conditions, one for the constant wall flux, the other for constant wall temperature. And now other thing is, when you define Reynolds number in internal flows, you have to be careful that you should use again another characteristic velocity called the mean velocity or the bulk velocity. So once again, what it means, if you replace your velocity profile with a uniform variation all along the cross section, okay, it should satisfy conservation of mass at that particular location. So the mass flow across this particular cross section in this profile should be equal to the uniform profile. So if you do that, you will get a definition for the mean velocity, which is something like this, which we saw yesterday, and based on that you define your Reynolds number. Okay, now for a circular cross section, of course you know this is the diameter of the cross section, but you can also extend this definition to non-circular cross sections, right. So if you have a duct with say rectangular or triangular or square cross section or some other cross section, so you have to define your Reynolds number based on what is called the hydraulic diameter. So you use hydraulic diameter, which is defined as 4 times area by perimeter. Okay, so if you have a rectangular cross section with dimensions, let me just so if I just tell you that this is your A and this is your B, okay, so accordingly this will be, so your area now will be what? This will be 4 times AB divided by 2 times A plus B, right. So this will be 2AB by A plus B. Okay, so this is how you have to replace your diameter with an equivalent hydraulic diameter and define your Reynolds number based on the hydraulic diameter. So this is for the case of non-circular cross sections. Okay. So now with sufficient understanding also we have classified the different regimes, whether it is a laminar or a turbulent, depending on the value of Reynolds number below a certain critical Reynolds number. Critical Reynolds number generally is about 2300. So below this value it is generally classified as laminar flows, and above this is generally considered as transition or turbulent, although this value may vary. In cases where you maintain a very uniform streamlined profile and your turbulent intensities are very low at the inlet and your valve is extremely smooth, you can delay the transition to turbulence to as high as 8000 or sometimes even 10,000. Okay, experimentally it has been shown that you can delay the transition. Okay, but this is a generic thumb rule. Okay. So today what we will do is we will take up first the region 3, okay, and in region 3 we will get the solution to the velocity and the temperature profiles. And now just before that I just want to write down the conservation equations for momentum and energy in region 3. Okay. So we will make certain approximations when it comes to region 3. So what are the approximations? So why we are looking at region 3 is it is one of the simplest to start with, because you can make several approximations so that your Navier-Stokes equations becomes much simpler, so you can get a direct exact solution to that. So directly you found du by dx is equal to 0, therefore your velocity is a function of, and you are now assuming, although this is a 3-dimensional flow, you are assuming that right now the profile is 2-dimensional. That means you do not have any dependence of velocity on the theta direction. So strictly speaking you have to write down the Navier-Stokes equation in the cylindrical coordinate system, because this is a duct with a circular cross section. Okay. So but you are neglecting the variation of velocity and temperature with the third direction, and also you are neglecting the variation with respect to the x direction, so it is a function of only r. Okay. And once you reach the fully developed condition, therefore in region 3 all your inertial terms get knocked off, because du by dx is 0, okay, and v velocity is 0, correct. There is no v velocity, there is only axial velocity, there is no radial velocity, there is no azimuthal velocity, so the inertial terms all disappear. Okay. So there is no, so you have your x momentum, r momentum, theta momentum. So r momentum and theta momentum are not there right now, only x momentum will be there, and in x momentum on the left hand side you have du by dx 0, vr 0, v theta 0, so your entire inertial terms disappear. So only you have your diffusion terms and your pressure gradient term. Okay. So therefore for this case your I will say vr and v theta, these are 0, and also variation, so this anyway I have said that u is a function of r only. Okay. So therefore the momentum will be only x momentum, so you have minus 1 by rho dp by dx this is your pressure gradient term on the right hand side, plus you have your diffusion term. Once again in the diffusion terms the variation, since your du by dx is 0, so your d square u by dx square will be 0, also the variation with the theta direction is also not there, therefore your d square u by d theta square is also 0. Okay. So the only term, what is the only term then which has to be included with respect to r? Okay. The diffusion term due to the gradient with respect to r, right. So that will be in the cylindrical system nu into 1 by r d by dr into r du by dr, right. So this is all in cylindrical system, this is not Cartesian. In Cartesian you do not have 1 by r, so if you write the Laplacian operator in cylindrical coordinate system you will get 1 by r d by dr into r. Okay. And the shear stress in the radial direction is du by mu into du by dr. Okay. So that mu divided by rho is your kinematic viscosity here, so this should be equal to 0. So this is a big approximation, okay. So that is why it is much simpler to look at region 3 because you are not including any of the inertial terms, okay. Only pressure gradient term balances your viscous forces, okay. So this is the very significant terms which are important in internal flows. In external flows for flat plate you can say that dp by dx is 0 because your free stream velocity is invariant of x, but here you have only these two terms and they have to balance each other. So you cannot say simply that dp by dx is 0. In fact the pressure gradient is driving the flow here, okay. So that is why internal flows are pressure driven flows, okay. So therefore they incur a considerable pressure drop to drive flow internally, whereas external flows, even if you use a fan or a blower for convection, so you do not have any pressure drop or very negligible, whereas in internal flows pressure drop is a very important parameter because to drive the flow you need a pressure drop, okay. So let us write down the energy equation. So the complete energy equation is your u dt by dx plus v dt by dr in the cylindrical coordinate system plus okay, so I call this as Vr v theta by r dt by d theta. This is your inertial term. So I am writing everything under steady state incompressible. These are the other approximations, incompressible flow. So this should be equal to the diffusion terms, that is 1 by r d by dr into r into k dt by dr. This is your diffusion term along the radial coordinate. So you have 1 by r d by dr r into qr is k into dt by dr, okay, plus you have d by dx of k dt by dx plus 1 by r square d by d theta into k into dt by d theta. So we are also neglecting what? Viscous dissipation. We have included everything, all the terms except the viscous dissipation term. Now once again for this case you can directly say, since you do not have Vr and V theta, so therefore the convective terms involving Vr and V theta are 0, right, and we have also said that variation of both velocity and temperature with respect to the circumferential direction is 0, correct. So therefore you have only one convective term involving the axial velocity, which is balancing your diffusion in the radial direction as well as diffusion in the axial direction. This is your axial conduction, this is your radial conduction. But once again we will make an approximation that compared to your radial diffusion or radial conduction, your axial conduction is very minor, because if you look at the profiles of temperature, the gradient is dominant along the r direction, therefore the diffusion will be much pronounced in the radial direction. So compared to the radial conduction we will also neglect the axial conduction term. So finally you are left with u dt by dx is equal to 1 by r, so 1 by r d by dr r k dt by dr. So this is your energy equation in region 3, okay. So now since we have written down the equations, we will go ahead and start solving them. So I will erase this. Okay, so let us call this as equation number 1, and let us start with the momentum solution first. See, also when you write down the y momentum equation, it comes out that your dp by dy is approximately 0 because all the other terms are negligible, right. So therefore p is invariant of y, it is only a function of x. Okay, so this is the conclusion. As far as your pressure is concerned, it is a function of x. Okay, so if you write the y momentum, all the inertial terms are 0, all the diffusion terms are 0, so that will leave with dp by dy is 0. Okay, therefore the pressure will be only a function of x, therefore you have pressure gradient only along the x direction, which balances the diffusion term, diffusion of velocity in the radial direction. So with that, why is that required? Because now this is a constant term, because if this has to balance this is a function of r, this is a function of x, so they both have to be constants, correct, then only this can balance this. So once this is a constant, that means we can directly integrate it out. So this is the simplification. Okay, so therefore since p is a function of x only, okay, so minus 1 by rho dp by dx should be a constant, right. Since you know this is a function of x, this is a function of r, they can balance only if they are constant, therefore we can integrate 1, integrating 1 with respect to r. So we get, if you integrate once, r du by dr will be, you have to now tell me. Which one? Correct, but dp by dx also has to be a constant, because this is a function of, p is a function of x, and this is a derivative with respect to x, this is a derivative with respect to r, and u is a function of r. So these two can be equal only if they are equal to a constant, that is the only possibility. Okay, so this will be nu by rho, rho cancels, this will be 1 by nu dp by dx. So therefore I can replace the partial derivative with an ordinary differential, because u is a function of only r and p is a function of x here. So I can say this is r, so there will be an r square by 2 right here, r square by 2 plus a c1. Okay, so now if I integrate it again, this will be 1 by nu, so my r cancels here, so this will be dp by dx, which is a constant, and if I integrate it again, this will become r square by 4 plus, this is c1 by r, if I integrate that, that will be c1 ln of r plus c2. Okay, so this is my solution. Now I have to find the constant c1 and c2. How do I find the constants? Boundary conditions. Okay, so what are the boundary conditions? So u at r equal to r naught. So what is u at r equal to r naught? If r goes to r naught, 0. And what is the other boundary condition? In the case of external flows, we can give a boundary condition where your u going to very large y to infinity, then your u becomes u infinity, whereas here you don't have anything like that. Exactly. So at r equal to 0, u should be finite. Now directly you can look at this equation, if r goes to 0, this goes to infinity. So in order to make u finite, c1 has to be 0. Okay, so directly this gives you c1 is 0. So you can use u at r equal to r naught equal to 0 to calculate c2, and if you do that, your final velocity profile comes out as Okay. So this is your velocity profile, and you can directly see that for a given pressure gradient dP by dx, for a fixed pressure gradient, the variation with respect to r is parabolic. Okay. So at r equal to r naught, this will be 1 minus 1 0, and at r equal to 0, this will be 1 by 4 minus 1 by 4 nu dP by dx into r naught square. Okay. So now we want to see what is the maximum velocity. So because when we draw the profile, we draw it like this, and we know that we are plotting it with a maximum velocity at r equal to 0, but let us show that the maximum velocity or centerline velocity is maximum velocity. Okay. So how do we show that? How do we show the location of maximum velocity? Yeah, so you take the derivative du with respect to dr, equate it to 0, and you will find that r comes out as 0. So that means the center line is the inflection point. Okay. So there could be a maxima or minima, of course there has to be a maxima here. So this is the region where, so u max is equal to u center line. Okay. So center line velocity is the maximum velocity, and the value of the maximum velocity here is 1 by 4 nu dP by dx r naught square. This is the value of maximum velocity. So now we will go ahead and calculate the other. The other is the mean velocity, which is 2 by r naught square integral 0 to r naught u of r dr. Okay. So if you substitute the velocity profile and integrate it, r naught square minus 1 by 4 nu dP by dx, these are all constant terms which can be pulled out outside the integral, 0 to r naught 1 minus r by r naught the whole square into r dr. Okay. So if you integrate it out, you will get minus 1 by 2 nu dP by dx into r naught square by 4. So which can be simplified to um is minus 1 by 8 nu dP by dx into r naught square. So therefore you see um is now a fixed value in the fully developed region, because dP by dx is a constant. So everything is constant, so therefore um is a constant value in the fully developed region. Okay. So this is your expression for um. We also found out the expression for uc. Therefore you can also write your u of r as this entire thing is nothing but uc. Okay. And you can see from this expression that your centerline velocity is actually twice of the mean velocity, right. So therefore you can express your u as twice of um into 1 minus r by r naught the whole square, which is also u center line 1 minus r by r naught the whole square. Okay. So this is how your general velocity profile is written as a variation in terms of r. Is it clear? Since you have already done this, I am not spending too much of time. You can just go and look into any fluid mechanics textbook and you will find the derivation. So any questions so far? So you can clearly see that at center line you have r equal to r naught, you have your center line, and from there you have a parabolic velocity profile distribution. Okay. So therefore we will find out other integral quantities. The important integral quantity we will define in internal flows is called the friction factor. Okay. In external flows we define the wall shear stress, and from there we calculated a non-dimensional skin friction coefficient Cf. Okay. The same way we can also define a skin friction coefficient, okay, but generally people refer to as we will show that we'll show that the equivalent of a skin friction coefficient is your Fanning's friction factor. Okay. So there are two different friction factors which are defined. So one which is more popular is your Darcy or your Moody friction factor. So named after these two people who have defined it, and it is defined as F is equal to delta P by half rho um square L by D, because here your L by D is also an important factor. So as far as your pressure drop is concerned, because dP by dx is nothing but delta P by L, so that has to be included as it is. Okay. So this is how your Moody's friction factor is defined. The other friction factor is also called Fanning's friction factor, and he defines it as so that is delta P by twice rho um square L by D. So you see the basic form is the same, it is only the factor. Here they use a factor of half, and here Fanning uses a factor of 2, and you will see why Fanning defined it this way is that for the fully developed internal flows, okay, so the Fanning friction factor exactly comes out to be the same as skin friction coefficient. Okay. So therefore he defined it in a convenient form where you can replace the skin friction coefficient which you are used to in the external flows, and that will become equal to your friction factor in the internal flows. Okay. So this can also be written as minus dP by dx into d by twice rho um square, right, because delta P by L is nothing but minus dP by dx. This is the pressure gradient. So since this is the pressure gradient keeps, so your pressure changes, is decreasing, therefore if you take a pressure gradient it will be negative, so therefore you have to put a negative sign here. Okay. So this is the way that you write it, and you can now substitute for dP by dx from this expression in terms of so your, let me call this as equation number 2. From equation number 2 you can write dP by dx in terms of um, correct, and you can substitute that here. So you will find that some of the terms terms will cancel off. So if you substitute that, this will be 8 nu into divided by r naught square, you have 2 rho square. Okay. So this should come out as 8 nu by rho r naught. Okay. So the cancels here, and okay, so this is d here, so d is twice r naught, right, and now you can define Reynolds number. Okay. So this is rho and this you can write as d naught by 2. Okay. So this will become 16 divided by Reynolds number. Similarly, if you had substituted here for the Moody's friction factor, this expression will come out as 64 by Reynolds number. Okay. So that is the difference, the factor is the difference. And now if you define your skin friction coefficient Cf for internal flows as tau by half rho square, okay, and your tau is nothing but minus nu du by dr at r equal to r naught divided by half rho um square. So you can calculate, you have the velocity profile, you can calculate the derivative with respect to r, and you have to calculate derivative at r equal to r naught, and you substitute it. So you will get an expression for Cf, which also comes out to be exactly identical to 16 by Red. So that is why the way the fanning friction factor was defined, both fanning friction factor and skin friction coefficient become identical. Okay. So therefore for the fully developed case, your Cf is equal to your F, let me call this as F fanning here to differentiate it from F Darcy. So this is another important result that you should remember. Okay, now if you plot the friction factor, I think all of you know how it looks. So this is called the Moody's chart, right? I hope all of you remember the Moody's chart in fluid mechanics. That is in internal flows, that is the single most important thing that you might have learnt. Okay, if you plot F as a function of Red. Okay, now remember, if you plot on a log scale, now this is a hyperbola, right? You have F, say F Darcy, F into Red is equal to 64. That is a rectangular hyperbola. So if you plot on a log scale, this becomes linear. Okay, so on a log scale, if you plot a log scale, so this will look, so with your increasing Reynolds number, the friction factor comes down, right? So this is your relationship, F is equal to 64 by Red, and this is valid for certain Reynolds number till what? Critical Reynolds number, you can say 2300. So once critical Reynolds number exceeds, the flow becomes turbulent, and the variation will not be as straightforward as this, it becomes completely different, and in the turbulent region you will find it is not a single line, but you will have multiple lines like this. Okay. So what these multiple lines indicate is the friction factor is not only a function of Reynolds number, but it is also a function of the roughness. Okay, so you plot what is called non-dimensional roughness, that is roughness height divided by the diameter of the tube. So with increasing roughness, your friction factor increases. So this is completely turbulent, whereas in the laminar flow you find a very linearly decreasing profile if you plot it on a log scale. So this is called the Darcy or Moody chart, from which you can pick up for a corresponding value of Reynolds number what is the exact value of the friction factor. Okay, I think all of you are familiar with this. In the case of non-circular ducts, okay, this is valid for a circular duct. Okay, if you go to non-circular ducts, so your friction factor F becomes 64 by some factor phi times Re. It is not 64 by Re, 64 by Re is only for circular ducts, because we have seen that we have substituted all this relation for circular ducts, but generally for non-circular ducts you have an additional factor phi, and this phi will be a function of the aspect ratio. So if you have a non-circular cross section, okay, you have aspect ratio A over B. Okay, so it is a function of this aspect ratio. Suppose you take a rectangular cross section, you can plot phi as a function of A by B. So say A by B going from 0 to say 0.5, and on the top scale say from 0.5 to 1. So you have a variation something like this corresponding to this, and you have a variation, another variation corresponding to a by b of 0.5 to 1. So you have typically variation of phi for a smaller range of a by b, 0 to 0.5 you have one variation, for a by b varying between 0.5 and 1. So at the limiting value 1, f becomes 1 basically. Okay, so then it becomes equal to a circular cross, a square cross section. Okay, so then you have the value of phi at somewhat approaching to 1 when your a by b approaches 1. Okay, so therefore you have to know this factor, and then you have to plug it for a non-circular cross section with a different aspect ratio, and that will give you the corresponding friction factor. So anyway, these are some additional details which you can find in textbooks. So next what we are going to do is take the heat transfer problem, so very quickly in another 5-10 minutes, and see how we can find the temperature profiles in the thermally fully developed region. Okay, now we know how the velocity profile looks. So now in region 3, temperature solution. So once you get the velocity solution for velocity profile, then naturally the next part will be to get the solution for the temperature, and I have already told you that the heat transfer coefficient is a constant in region 3. So we have to know what is the value of this constant. So therefore first we look at a boundary condition which will be the uniform wall flux, that is q wall double prime is a constant. Okay, now we have already defined my d by dx of theta, and theta is t minus t wall by tm minus t wall. This is equal to 0 for thermally fully developed case. So we will expand upon this term. Okay, so if you differentiate it by parts, okay, how, so what do you get? So this is v du minus u dv by v square, right? So if you differentiate and expand it, you can just try, I will give you some time, you should be getting an expression like this. So all of you please try expanding this differential here. Okay, so maybe you can complete it as a homework, but you should be able to get, very straightforward, you should be able to get this. Now the important fact is, when you apply the uniform heat flux boundary condition from the Newton's law of cooling, you can say that q wall double prime is h into delta t, t wall minus t mean. So since your wall flux is uniform, therefore dq by dx will be 0, right? There is no variation with respect to x, and therefore this will give that dt wall by dx should be equal to dt mean by dx. Very important conclusion, because coming from the fact that you have a uniform heat flux. So therefore if you look at the profiles, if you substitute, let us call this as now number 1, this as number 2. If you substitute this conclusion, that is dt wall by dx should be equal to dtm by dx, what happens? these two terms will cancel out. So therefore you directly get the fact also that dt by dx should be equal to dt vol by dx, which in fact it's equal to dtm by dx. Okay. So the slopes of all the three profile, like your any temperature at any location, radial location, your wall temperature and your mean temperature, they are identical, and it can be true only. So how should the profile look? If you plot your temperature on the y axis and x, if I want to show temperature at any radial location, wall temperature and mean temperature, and if the slopes have to be the same, it has to be exactly parallel, all the three have to be parallel, and in fact we will see that this has to be just linear. Okay. So you can say then this is your T wall, okay, this is maybe T at some radial location, and say this is your T mean. So this is a function of x, this is a function of r and x, this is a function of x, but all of them in the region 3 will be linear, okay, and the slopes are identical. Okay. So this is a very important conclusion which characterizes a fully developed flow with a constant heat flux boundary condition. So therefore if you apply this fact to the energy equation, okay, so what was the energy equation that we had written? We had written, if you u by alpha dt by dx. Oh, okay, there is one more thing, I forgot rho Cp on the left hand side of the convective terms. In the when you wrote the energy equation, there should be rho Cp. Okay, on the right hand side you have k. Okay, so I am taking rho Cp by k, which is 1 by alpha dt by dx should be equal to 1 by r d by dr r dt by dr. Now the fact I am going to use here is my dt by dx is exactly identical to dtm by dx. So these are all just a constant. Okay, so this can be true only if they are all constant, because t is a function of both r and x. If this slope has to be equal to this and this has to be equal to x, dt wall by dx, the slope has to be a constant value, and therefore it is a linear variation. Okay, so this is an important fact. You can just replace this as dt mean by dx. Now this is a constant, so therefore you can see that you can now integrate this equation with respect to r just like the way you integrated the velocity profile, because now this term is a constant and therefore this does not become a partial, this can be written as an ordinary differential equation. Okay, so I will just give you the result of the integration and we will stop there. So if you integrate this equation, you will get solution for t as a function of dt or dtm by dx 1 by alpha dt by dx, and you have to also substitute the parabolic velocity profile which you obtained from the fully developed hydrodynamic solution. So then you integrate it with respect to r, so you get so this is your temperature profile. So we will stop here for today. So tomorrow we will continue from here, apply the boundary conditions and calculate the constants, and also similar to calculating integral quantities for velocity like skin friction coefficient and friction factor, we will calculate the heat flux, and the heat flux anyway is a constant, we will calculate the heat transfer coefficient, and we will know what exactly the constant value is.